Hello, everyone. I'm Zeke. So, when I was 8 years old, I wanted to know how to contact an astronaut on the International Space Station. And as it turns out, they have a ham radio up there. So I got my ham radio license and started building my own homemade antennas and satellite tracking systems to be able to contact it. Now, this is a Lego prototype satellite tracker that I made, and it uses potentiometers for position sensing. And I used it to test my code before putting it onto my full-size satellite tracker here, which also used potentiometers. I used this to contact the ISS repeater. Now, the way this works is I send my signal up to the ISS, and it retransmits it back down to other people on the ground. And each one of these pins represents a person that I've talked to through the ISS repeater. So the farthest people who I've talked to is someone in Nashville and another guy up in Alaska. And I'm based here in Portland. So the problem was, I wanted to talk to an astronaut, and astronauts have other things to do. They can't be sitting on the radio all day answering calls. And that's where AIRS came in, Amateur Radio on the International Space Station, who are NASA's educational outreach program. And they schedule calls between students and astronauts so that we can contact them. So I submitted an AIRS proposal to use my homemade equipment to contact an astronaut. Now, in December of 2023, I heard about the Oregon State Science Fair, NWSC. And because I heard about it in December, that meant that I only had 3 months to complete my project, a 3D printed desktop satellite tracker. Now, why 3D printed? Well, all my other satellite trackers, like that prototype that you saw, were made out of Legos, so I wanted to try something new. But the problem was I didn't have a 3D printer and I didn't know how to use one. However, I was able to make the 3D design of it. Now, this is a planetary gear system, and I use it to slow down the speed of the motor from 400 RPMs down to a more manageable 17. When I did get my 3D printer, it had a very steep learning curve, so each one of these 3D prints is an attempt I made at the tracker before it actually worked. There's probably about 80 in there. Now, those potentiometers that you saw for position sensing in the first slide are okay, but they have a big problem, and that's because they don't rotate forever. So to fix this, I'm replacing them with these two components, a magnetometer and an accelerometer. Now, what are they? Well, a magnetometer is basically like a compass, and no matter how many times you rotate a compass, it never twists up. You can rotate it as many times as you want. And the accelerometer is just like it sounds. It measures acceleration, so it's really just telling you where down is. So I will use the magnetometer for azimuth positioning sensing and the accelerometer for elevation. Okay, so we can now replace our potentiometers. Great. Now notice the scale of these components here. That's 1 millimeter. And you might think that these are very hard to solder on by hand, but they're actually some of the easiest components to solder because they have little balls of solder on each of their pads, which are only 0.25 millimeters apart. So all I have to do is add a little bit of flux paste onto the board, place it, and then heat it up, and it will snap into place because of the surface tension of the solder. And now we move up to more of the circuitry for the desktop satellite tracker. So this is the baseboard, and you can see I have a few components on it. I have my ESP32 microcontroller for calculating the position of the satellite that we want to track and determining where I want to position my antenna to point at it. I have my serial control here, and I'm using this to be able to talk to it and tell it where to track. I have an LCD screen here to display satellite telemetry and select the satellite to track using these buttons. I also have this GPS module here. Now, why do I need a GPS module? Well, that's because the two-line elements, or TLEs, that I use for getting the position of the satellite only give me XYZ positioning from the center of the Earth. And so I need my position on the ground to calculate where to point my antenna to point azimuth elevation at the satellite. Now, there's 3 prongs here, and on the bottom of them, they have these battery contacts, which each have 4 connections. And the reason this is important is because they press onto the circle board here. Now, the whole point of the magnetometer was to make it so that I can rotate it as many times as I want. But there's still electronic components, which means that they need power. And wires that would normally be used to transfer that power they can twist up. So to fix this, I use this circle board, which acts as a slip ring. And no matter what position they're in, we can always get power to these 4 contacts here. And a FPC connector, or flexible PCB connector, goes there, and that's where the flex board connects. So this is the flex board, and you can see the magnetometer and accelerometer there. And it bends to all the places that I need it to bend, and you'll see that in the next slide. Now, there are a few problems that I had when I was making this, and one of those problems was that my traces would constantly crack on places like this. And this is a big problem because it means I can have intermittent connections. Now, this was due to a few reasons. 1, the flex board bending, like it's supposed to. 2, this is actually a cutout here, so it's meant to bend on the cutouts, and you'll notice there's a cutout right there. And 3, the weight of the motors, because they are very heavy. So to fix this, oh, and there's also a hard junction here. So to fix this, I gradually increase the size of the trace into the size of the pad, so that there's no more hard junction and it can't break anymore. And we just do that to all of the connections. So now I want to talk about some more of the problems that I had with the flex board. And you can see how it bends there. So some of the problems I had were my pads would come off when I would solder the motors on, because they're the only through-hole components. And my coverlay would actually melt over the surface mount components pads when I would solder them on. So to fix the surface mount component, to fix the pads for the motors just tearing out of the board, you can see originally there's nothing keeping this small pad from just pulling out of the flex board aside from these 2 tiny traces. And to fix this, I increased the size of the copper to be this big now, and it's actually held in by the coverlay, so it can't pull out of the board anymore. To fix the melting coverlay, I was using way too much heat, so I need to just use less than 250 degrees C for the surface mount components, and no more than 300 degrees C for less than 5 seconds when I'm soldering the through-hole components like the motors. Otherwise, the traces will crack and melt and bad things. I know that my potentiometers were fairly accurate, but I wanted to test the accuracy of my magnetometer and accelerometer. So I tested the accuracy of it with another magnetometer, a phone compass. And the greatest error I had was when it was pointed east with -7 degrees. That's acceptable. So now to test my accelerometer's accuracy, the first thing I do is I level it, and then I rotate it up to where it measures 90 degrees, and I calculated that its error is 14.2 degrees. That's quite high. It's more than double what the magnetometer's was. But I can fix this by manually rotating it up to 90 degrees and then interpolating between where 0 actually is and my new 90, and then that will give me very accurate positioning with no error. At the science fair, the desktop satellite tracker won quite a few awards. So it won first place in the engineering category and best of fair in middle school. And at the National Science Fair, Thermo Fisher JIC, it got second place in the math category. Also, by the way, the AIRS proposal was accepted, which means that I have to start working on the technology to be able to contact the International Space Station. So this is the full-size tracker, and it's basically a scaled-up version of the desktop satellite tracker, especially because it uses the same baseboard and circle board slip ring technology. And it also uses a magnetometer and accelerometer for position sensing. The main difference with this is that it's more robust and it's waterproof, because I'm going to use it outside. You can also notice that instead of having a planetary gear system, I'm directly connecting the azimuth rotor to the base. And the reason for this is I just don't need a planetary gear system to gear it down, because these motors spin at 0.5 RPMs. So it takes 2 minutes to go a full circle. So this is a comparison between the desktop satellite tracker and the full-size tracker. And on the full-size tracker, there's no antenna, but on the desktop satellite tracker, you can see how it's just on top there. So where is it for the full-size tracker? Well, there's actually a 10-foot long 2x2 post that goes through the center of it with an antenna on either side, and you'll see that in a few slides. Now, the baseboard for the desktop satellite tracker is there, but where is it for the full-size tracker? Well, if we open up this section, we can see that it is in there, and that's what it looks like. If you're wondering what all this shielding is around the outside, I'll get to that in a minute. It's kind of an interesting story. So now I'm led a workshop to teach students from my school, Teach Northwest, how to build the cross-Yagi antennas that I would use to contact the International Space Station. And I'm teaching them to build circularly polarized cross-Yagi antennas, and that's because I don't know what orientation the ISS is going to be in, so I have to be able to contact it no matter what orientation it's in. And even, so now you can see how the antennas are set up there. And now I'm going out to the location where the contact would take place twice a week to test my antennas and setup before the actual contact. And even 10 days before, I wasn't sure if it would work because I had an immunity problem where the transmitting RF from the antennas would interfere with the weak I2C communication of my sensors. And that's what that shielding was that you saw. So I had my grandma sew a 10-layer RF shield out of RF fabric here to just encase the satellite tracker. And this is what it looked like.
Can you wear that?
It has no head.
Oh,
And this is the tracker, by the way. So it would wear this, and then the post would go through these. And that mostly fixed the problem. So now, on October 18th, 2024, it was finally time to attempt to contact the International Space Station. So many things had to go right for this to happen. I only had one shot while the ISS was passing overhead for only 10 minutes because it's traveling at almost 18,000 miles an hour, and there's no time for troubleshooting. At 7:30 a.m., there's an empty field, and everything has to be set up from scratch because in just a few hours, the ISS passes over the horizon at 11:28. There are 100 people on site and 400 people waiting on the live stream, including live TV crew who are filming it. The clock on the satellite tracker has to be synchronized to the second because the two-line elements that I use to get the position of the satellite are use the time to calculate the position of the satellite. The GPS coordinates have to be correct because, as I talked about, it only gives XYZ positioning, so I have to figure out where to point my antenna as L. My two-line elements have to be up to date because if they're wrong, I'll just completely miss the contact. The RF shield has to eliminate the interference because even though it mostly worked, it was not 100% because we were transmitting at 100 watts. So the magnetometer and accelerometer needed correct data. Especially the magnetometer couldn't have any magnetic interference, otherwise that would completely throw off its reading, and we would just point in the wrong direction. The homemade noise amplifier had to not only amplify the signal from the ISS, but it also had to turn off while I was transmitting, so I didn't fry it, which happened a couple times. The Doppler shift had to be manually tuned because if I drifted too far away from the signal of the ISS, it would just start to get weak. There couldn't be any feedback from the soundboard because I actually had to be able to hear it. And the signal also had to get around a nearby building. And this was unfortunate because the ISS happened to be passing right above right behind that building. So 1 minute after the ISS passes over the horizon, and all we're hearing is static. There's no signal from the ISS. So it's 11:29 and it's just static. 11:30, 2 minutes after the ISS passes over the horizon. It's still just static. There's no signal from the ISS. Is it working? Anyone SS? Anyone SS? Anyone SS? This is Kilo Juliet 7 November Lima Lima.
Kilo Juliet 7 November Lima Lima. November Alpha 1 SS. Over.
Sunita, this is Kilo Juliet 7 November Lima Lima. It is a great honor to connect with you today. I read you 5. Hold on, there's more. Okay, after the contact, the students were actually able to get all of their 20 questions in during the 8 minutes of the contact because we missed the first 2. This was also the very first homemade AIRS contact to use completely homemade antennas and satellite tracking systems, since it started in 1996. It was also the first ever contact or satellite tracker to use magnetometers and accelerometers for position sensing, so that was new too. If you have any questions, now would be a great time to ask them. Thank you. Yeah?
What were you synchronizing the time against?
So I was synchronizing the time against Unix time. So I basically opened up a terminal, and I also have a GPS on here, but this was the other way that we were doing it. So yeah. Caps lock. Okay, something like this.
Plus.
Anyway.
Plus.
Oh, okay. There's Unix time. Okay, that we enter that into the satellite tracker, and then that gives it its date.
Okay, did you consider pulling the time off the GPS module using that?
Yes, we also did that too.
Okay.
But we had to do that first because this RF shield blocked.
Okay.
There you
Yeah.
go.
Gotcha.
Yeah, grandma.
Yes?
So you manually compensated for Doppler. What
Yes.
did you use as a reference for?
Preset configured values in the radio. So I was manually turning the knob to change the Doppler shift if it drifted.
So knowing that straight up ahead was 0.
Yep.
So
Yep.
What radio, you said 100 watts, so is that a 9700 with
Yep.
satellite? Oh, yeah, good.
What connector were you using for your slip ring connection?
Okay, so that was using battery contacts. So on the bottom here, I have battery contacts,
Nice.
and they press onto the.
Did you look at the wear on it after?
Yeah,
using
it has survived for a very long time.
Very cool.
I've taken it to several conferences and it's still working. So
It's amazing.
yeah.
Have you used it a second time successfully?
Not this one, but the desktop satellite tracker has worked quite a bit. Yes?
I want to make sure I heard that correctly, that you had RF troubles in the I2 C bus. There's some over.
Yes, exactly. So my I2C had a problem where the 100 watts transmitting from the antennas would just interfere with them. And then I would not be able to read the data off the sensors, and I wouldn't be able to tell its position, and then the chip would lock up. So our backup for this, if the shield didn't work, was to power cycle it, and then have it automatically resume tracking after I was done transmitting.
Very quick follow-up question. Was that G-Predict?
No, I have my own code here for,
Oh, no, the satellite tracker.
Oh, yes, I have my own code for
That's all.
tracking it. Yes, that.
Easy.
So you take the TLEs and you do the calculation?
Mm-hmm.
Yeah, including your GPS location.
Yes.
So center of the earth to you to the satellite.
Mm-hmm. Yeah, I'm using Neoclese's 5B4AZ. It's a C library that gets the TLE data and gives a. It's either XYZ position or it's as L. So, yeah.
what's next?
What's next? Well, if you've ever worked on a project for almost half your life, you'll know that after it, you need a little bit of a break. But I do have plans. Like, I've had an idea where I can make a octocopter that goes up 400 feet in the air with a phased array antenna on it. I've also had ideas to make a hexcopter, that's what I'm calling it, that can transport 4 people and land in a parking spot. So, automatically.
That's the next science fair.
The next science fair project.
Battery powered cruiser company?
Yeah, something like that.
There's some cheap Teslas available.
Fire sale.
Any other questions? Yeah?
So do any of the ISS tracks duplicate themselves, or each one is a one-off?
So the
Eventually they might overlap.
yeah, they might overlap
Someday.
eventually, but they do drift every day. And there's a bunch of ISS passes about every 12 hours. So there's like 12 hours with ISS passes, and then 12 hours just not being able to see them over the horizon.
It's like 6 or 7 in a row
Yeah,
that they process.
yeah.
The reason I asked, by gathering the data of that track, if I wanted just to plant my tracker in my backyard using the data, I could simplify the thing basically with a couple of spring-mounted, clockworks. They basically started.
You might be able to, but you'd only be able to do one pass.
Exactly.
Yeah.
Do you happen to know how often they increase their altitude, because the ISS continuously lowers in altitude?
So I know
periodically?
they do station keeping burns because of the atmosphere.
Yeah.
I don't know how often they do that.
Thank you.
Yep.
Have you got to hear from the astronauts again since the last time you talked to them?
No, I haven't. But I heard she's back, so.
They spent a lot of time on it.
Mhm.
Unplanned.
Yep.
Is it open source?
Yes, it is. So I have all of the design files. They're on my YouTube channel. So look at my newest video in the pinned comment in the description.
What's your YouTube?
Oh, I should probably put that up here. You know, it's this. It's my call
It's your
sign.
call. Okay, great.
Yeah. This is.
It's an old picture.
Yeah. It's a very old picture. Anyway, this is my YouTube channel. You can find a lot of stuff about my project here.
Awesome. Thank you.